Hello, and welcome to our channel. Today, we are embarking on an extraordinary journey to answer one of the most profound and fascinating questions in human history. How did our universe begin? Where did it come from? And how did it become what it is? The Big Bang Theory is the most widely accepted and evidence-backed theory in the scientific world to explain the origin of the universe. It proposes that about 13.8 billion years ago, the universe suddenly began to expand, starting from an incredibly small, infinitely dense and hot spot. This monumental event started the process that laid the foundation for the existence of stars, galaxies, planets, and even us humans. Throughout history, many scientists have tried to solve this mystery. Edwin Hubble, for example, laid one of the cornerstones of this theory by discovering that the universe is expanding. Albert Einstein's general theory of relativity helped us understand the dynamics of the universe, while pioneers like Georges Lemaitre first proposed the idea of the Big Bang. But how did this theory develop? What evidence supports it? And what does this epic story of the universe tell us? If you are ready, let's embark on this cosmic journey together and discover the secrets of the universe step by step, down to the last detail. One of the most powerful and striking proofs of the Big Bang Theory is the cosmic microwave background radiation, or CMBR for short. This is defined as a weak radiation that reaches from the early universe to the present day and can be detected in every corner of space. But what is this radiation and why is it so important? The CMBR is a remnant of the extremely hot and dense conditions of the universe just after the Big Bang. About 13.8 billion years ago, when the universe was still very young, the temperature was incredibly high and energy was everywhere. But as the universe began to expand, this energy cooled down, leaving the microwave radiation we detect today. CMBR is almost completely homogeneously distributed throughout the universe, but with very small temperature differences, which sowed the seeds for the formation of galaxies. This radiation was discovered by chance in the 1960s by Arno Penzias and Robert Wilson. Working with a radio antenna, the two scientists noticed a constant noise and realized that this noise was actually a trace left over from the birth of the universe. This discovery revolutionized the world of science and earned them a Nobel Prize. The CMBR is considered a fundamental piece of evidence supporting the veracity of the Big Bang Theory and has radically changed our understanding of the origin of the universe. In our images, you can see in much more detail the distribution of the CMBR in space, how it cooled as the universe expanded, and the place of this discovery in the history of science. The first seconds after the Big Bang were one of the most chaotic and exciting periods of the universe. At this stage, the universe was incredibly hot, dense, and full of energy. The temperature reached trillions of degrees Celsius, and in these conditions, matter as we know it today could not exist. Instead, the universe was filled with fundamental particles, quarks, and gluons. These particles had such high energy that they moved freely, creating an exotic state of matter called a quark-gluon plasma. But as the universe continued to expand, the temperature and density rapidly decreased. In a tiny fraction of the first second after the Big Bang, quarks came together to form more familiar particles like protons and neutrons. This was the first step in the emergence of the fundamental building blocks of the universe. Then, within a few minutes, these protons and neutrons began to combine to form the first atomic nuclei, especially the nuclei of light elements. This was a critical stage that laid the foundation for the material structure of the universe and the origin of everything we see around us today. These incredible conditions are hard to imagine, but scientists are able to partially recreate these moments in the laboratory. Huge machines like the Large Hadron Collider at CERN, for example, simulate these early universe conditions and offer us clues. In our images, you can follow these incredible processes step by step, from quark-gluon plasma to the formation of protons and neutrons, and better understand how the early moments of the universe took shape. As the universe continued to expand, a crucial milestone was reached after about 380,000 years: the formation of the first atoms. In the time since the Big Bang, the temperature of the universe had dropped so low that electrons could no longer roam freely, but instead fuse with atomic nuclei. This process is called the recombination epoch in the scientific world and is a revolution in the history of the universe. Before this event, the universe was a dense plasma and light was constantly scattered by free electrons. Therefore, the universe was covered in a thick fog and was not transparent. But when electrons combined with nuclei to form the first atoms, especially hydrogen and helium atoms, this fog lifted. Light could now move freely and the universe became transparent. This symbolized the transition of the universe from a period of darkness to light. At the same time, this process also gave rise to the cosmic microwave background radiation, because light could now propagate unimpeded. These first atoms later became the basic building blocks of stars and galaxies. Hydrogen and helium in particular made up most of the universe and triggered the birth of the first stars. So the universe slowly began to evolve into what it is today. This period was a critical step in shaping the physical structure of the universe and offers us important clues about the early universe. In our images, you can see step by step how atoms formed, how the foggy structure of the universe dissipated, and how this great transformation illuminated the universe. Gravity was perhaps the greatest architect in shaping the universe. After the formation of the first atoms, as the universe continued to expand, gravity kicked in and began to gather clouds of gas together. These gas clouds were mostly composed of hydrogen and helium. Under the influence of gravity, these clouds collapsed and heated up as they were compressed. This process eventually triggered the birth of the first stars. The stars generated energy through nuclear fusion, turning lighter elements like hydrogen into helium and then into heavier elements. This fusion process increased the elemental diversity of the universe and laid the foundation for elements critical for life, such as carbon and oxygen. Over time, these stars came together to form galaxies. For example, the Milky Way galaxy emerged from this process as a gigantic structure made up of billions of stars, and our solar system is located in a small corner of this galaxy. The life cycles of stars have also played a major role in the evolution of the universe. Some of them were destroyed at the end of their lives by massive supernova explosions. These explosions contributed to the formation of heavy elements such as iron, gold, and uranium. These elements, scattered from the explosions, were then used in the formation of new stars and planets. Thus, the chemical richness of the universe gradually increased, and the galaxies we admire in the sky today are the product of this long and complex process. In our images, you can see in minute detail how stars and galaxies were born from gas clouds, how nuclear fusion shaped the universe, and how supernovae contributed to this story. Our universe has been expanding since the Big Bang and is still expanding. But observations made in the 1990s revealed that this expansion is not happening at a constant rate, but is accelerating. Behind this surprising discovery lies a mysterious force called dark energy in the scientific world. Dark energy makes up about 68% of the universe and acts as a driving force that accelerates galaxies moving away from each other. But where will this expansion lead, and how will the future of the universe take shape? Scientists propose several different scenarios for the fate of the universe. The first scenario is known as the Big Freeze. According to this theory, the universe will continue to expand forever. Stars will go out one by one, galaxies will disintegrate, and the universe will become cold, dark, and empty. Another scenario is the Great Collapse. In this theory, the expansion will stop at some point and the universe will collapse in on itself, perhaps to be reborn in a new Big Bang. Which scenario will happen depends largely on the behavior of dark energy and the total mass of the universe. Dark matter, which makes up about 27% of the universe, also plays an important role in this process. Dark matter holds galaxies together through gravity, while dark energy accelerates the expansion. These two mysterious elements remain the great unknowns shaping the structure and future of the universe. Scientists continue their observations with new telescopes and space missions to solve these questions. In our images, you can examine the expansion of the universe, the impact of dark energy, and these possible future scenarios in the finest detail. The Big Bang Theory is not just an idea, but a robust model supported by a wealth of scientific observations and evidence. The first of these evidences is the expansion of the universe discovered by Edwin Hubble. Hubble's law shows that the speed at which galaxies are moving away from us is proportional to their distance. Light from distant galaxies becomes longer in wavelength through an effect called redshift, a clear sign that the universe is expanding. The second big piece of evidence is the abundance of light elements in the universe. The proportions of elements, such as hydrogen, helium, and lithium, formed in the first minutes after the Big Bang, are in complete agreement with the predictions of the theory. Third, the cosmic microwave background radiation confirms the theory as a trace of the early universe. The homogeneity of this radiation and its small temperature fluctuations provide critical data to explain the formation of galaxies. In addition, supernova observations made in the 1990s proved that the expansion rate of the universe is increasing and that dark energy exists. These observations revealed that the universe is not only expanding, but that this expansion is accelerating. All this evidence places the Big Bang Theory in an undisputed position in the world of science. But science is not a static field. Every new discovery strengthens the theory or raises new questions. In our images, you can see in much more detail how Hubble's law works, the redshift effect, the abundance of elements, and how supernova observations contribute to the story of the universe. In this video, we explore step by step the basic principles of the Big Bang Theory, how our universe began, and how it came to be as magnificent as it is. This incredible story, which began around 13.8 billion years ago, ranges from the origin of the universe to the formation of galaxies, from the birth of stars to the uncertainty of the future. Humanity has been trying to answer these big questions throughout history, and science is getting one step closer to solving this cosmic puzzle with new discoveries every day. While the Big Bang Theory is the most powerful explanation we have, the secrets of the universe are still not completely solved. Future telescopes, space missions, and scientific studies will further deepen this story and perhaps provide more definitive answers about the fate of the universe. We hope this video has helped you better understand the origin, evolution, and possible future of the universe. Thank you for joining us and being with us on this epic journey. We hope to see you in the next video to explore more cosmic mysteries together.